Yeah, hello everyone, and welcome to another ICTS virtual string seminar. We are happy to have Derek Teaney from Stony Brook University with us today, and he's going to talk about transport and hydrodynamics and almost the chiral limit. So yeah, over to you, Derek.
Okay, so thanks very much for the invitation. Someday it will hopefully not be virtual and we'll meet in person again. And we probably wouldn't have this seminar if it wasn't virtual, so that's a good thing too. Okay, so I actually gave a somewhat more appealing title. So the title is actually From Non-Abelian Superfluids to Soft Pion Production, but it's actually the same talk. All right, so this is based on work that I did with Eduardo Grossi, Alex Soloviev, from my student Figlita Jan, and Juan Torres Risson, which isn't out yet. Okay. So, okay, sorry, 1 second. Okay, so I come from a somewhat different community. I was sort of assuming that most of you are not heavy ion physicists. I'm mostly concerned in my life with what happens when you collide two heavy nuclei together and produce a lot of particles, and sort of only tangentially interested in more formal aspects of theory. So I will give just a very brief introduction to heavy ion collisions. I see only one heavy ion person. I see Rajiv Bolero online, who we wrote a paper some years ago together. So let's just talk a little bit about what happens when you collide two nuclei together and create quark-gluon plasma. Okay, so the nuclei are collided at very high energies. The gamma is, over 1,000, right? And so the nuclei are very much length contracted. Okay, so the gold nucleus, very much length contracted.
Hello,
yes?
Derek, may I interrupt you? Can you make the screen full screen so that it's visible?
It actually is full screen, but okay, let me. Okay. Is that not full screen?
The slides are not visible.
Keep Tirtho in the email chain, please.
Okay, so you see the frame and
it is totally okay with me. It is totally fine with me.
Yeah.
But is that not full screen? Oh, I can
yeah, I think you can continue.
Okay, is that better? Okay, I continue. Is that all right?
So this is worse. Like maybe you can show us in the window only, but now part of the slide is not visible.
Part of the slide is not visible?
Yeah.
Okay. Stop sharing. Okay, 1 second, okay? Let's,
Yeah, sure.
Okay. I know what the issue is, okay? Okay. Now, let's try it again here. Sorry, everybody. Okay. Share. Okay. And then this is now very vanilla and should work. Does that, you don't see my full screen here?
Perhaps, Derek, can you change the slides? Can you go to the next slide?
Yeah. First of all, I'm freezing here. Why is it not?
I think your slides aren't updating for us as well.
Okay, escape. All right, let's try one more time, okay? Okay. Okay, you see my screen properly? Now you should see the Adobe Reader.
Yes.
Okay, and now if I hit full screen, you should see the full screen. Yes? Hello?
No,
it's
we see a
black
dark screen.
You see a dark screen.
Yeah.
Yeah, maybe we can go back to the
What,
window.
what,
I think
yeah,
this
but
has to work.
maybe I can hear. Look, I mean, this just has to do with my, let's try now. Do you see that?
No, it's still dark.
Still dark.
Yeah.
I have, okay, 1 second, stop it again. Okay, I don't, give me 1 more second, 1 more second. Okay. How's that?
Yeah. Now it's perfect.
Okay. Okay.
Thanks, Derek.
Great. All right. Sorry about all that. Okay. So, all right. So, okay. So my main interest is in colliding heavy nuclei. Okay. When two nuclei collide, their length contracted by a factor of 1,000 or even more. Okay. So this is the radius of gold. It's 15 Fermi across. Okay, and the two nuclei come in and they collide and they go bang, right? Okay, and so what happens when two nuclei, actually they don't really go bang, okay? So they essentially pass through each other at very high energy, okay? So that was my little graphic here. So you have two nuclei essentially just pass through each other and they leave behind, you know, a small fraction actually of their total energy in the central region, which is kind of expanding rapidly. This is hot QGP. Of course, then the system expands and you get particles flying off in all directions, about 20,000 particles in total in a central LHC event. And, you know, then you can go and measure all of those things, all of those particles as they fly off, okay? And you can measure their angles and momenta and so forth. So everyone got a clear picture of the geometry. So of course, this is really a theorist's view of what the detectors look like, okay? So the real thing looks something more like this, okay? So this is a picture from the Elise detector of all the particles flying out. This is the beam direction here, okay? About 20,000 in total, right? So, so let's talk about it just a little bit more, okay? So we're not going to spend too much time on it, but let's just sort of say why we think that why hydrodynamics is a useful tool to describe heavy ion collisions, or what was the experimental evidence for it, okay? So hydrodynamics has become the kind of standard model of heavy ion physics, And let's just say what the main evidence for it is, okay? So what is seen from like typical heavy ion collisions is the flow of energy, which is, you know, so this is clearly not circularly symmetric. This is not a theory plot. This is a, you know, event display of the energy per angle, azimuthal angle, around the beam, okay, in the CMS detector. And you see, you know, very clearly this sort of oblong shape. Now, sort of what has been, you know, confirmed over many years is that the origin of this, you know, anisotropic flow, if you will, is the following picture. So the two nuclei collided. So here's my two nuclei, which were length contracted. They collided. They leave this region of hot material. Okay, and then there was pressure gradients which were built up here, right? And so the pressure gradients are greatest this way and this way, and then the whole system expands along these arrows, okay? And that is the origin for this asymmetry in momentum space that you see in the final results. Okay, so for hydrodynamics, you're going to need basically that somehow the typical relaxation time compared to the CS's should be in the denominator, right? The typical relaxation time compared to the expansion rate, okay, should be much, much less than 1, okay? So that's, you know, this typical collision, typical condition. And if you express kind of typical relaxation time in sort of more of the fluid parameters, E over S, okay, it's kind of E over ST, then you're going to, you know, in practice, you know, this isn't way less than 1, but it's significantly less than 1. It's about 1/10, okay? So, well, 1/10 is small enough that you can start to use hydrodynamics effectively. Okay, and now there's, you know, fits. People do hydrodynamic fits, so they run hydrodynamic simulations, including me, and they describe, you know, this anisotropic flow, the distribution of energy, which is a function of angle, and they do it these days quite well, okay? Right, so those kind of fits give you a typical E over S. This is kind of tangential actually to the talk. A typical E over S of 1 to 3 times this quantum bound that you get from ADS-C of t. So the typical relaxation time, say E over ST, is 1 to 3 times h bar over 4 pi t. So it's about, you know, 1 to 3 times the quantum bound, okay? And these days this number is getting increasingly precise, but I didn't want to go into the details of, you know, how close or anything like that. Okay, so maybe just before we continue, let's just look a little. I mean, you should realize how amazing this is, right? So I mean, people never expected to see something like that. Okay, and in the early days it was difficult to see because of some experimental reasons, but these days there's sort of beautiful imagery and you really don't need any theory to talk about it. Okay, so this just, let me give some more imagery. Okay, so this is the event display, again, the head-on event display of the CMS detector, and this is the energy per azimuthal angle. Okay, and so in this particular event, okay, this is one event, right? In this event, you know, you really see this very flow pattern coming out there of the energy flowing out at different angles. Okay, and so I draw here a little schematic of what's going on. So in this event, you had a collision. The impact parameter was along this direction. Okay, and the material was flowing out this way and that way. Okay, so it's really a very, very strong signal even from one event. All right. Now, if you look also at other events, okay, so let me go give a little tiny bit more imagery, okay. So if you look at other events, so this is another event, you see not a dipole or a second harmonic pattern, but actually a third harmonic pattern. So you see this kind of third harmonic pattern. You have sort of 3 outward flowing shapes of matter. So what's going on there is that you see the initial energy density is fluctuating from event to event, right? So it's not at all smooth. Well, it's partially smooth, okay? Then those fluctuations lead to pressure gradients like this way and this way and this way, okay? And that leads to a flow of energy in the given event, which is sort of triangular in shape, okay? So we can, and this is really a kind of head-on collision. And so you really can see this nice sort of angular flow of energy reflecting not just the second harmonic, but also the third harmonic and so on, okay? So this has become a huge, huge machine, okay? Where people measure the second, third, and fourth, and fifth, sixth, okay, seventh harmonic, okay? What you see here is these were just one event, so you can ask yourself, like, what is the probability for having such an event, right? And so hydrodynamics predicts, like, the probability to having this event versus that event, how large it is from event to event, okay? Also, the nonlinear mixing between the different harmonics is also predicted. And in summary, like, it's just way beyond my wildest imagination, okay? It's incredibly successful. It predicts, you know, all of these harmonics, their fluctuations, the probability distributions, you know, many, many things, their dependence on centrality and so forth. Okay, and that's sort of say what's going into this statement that in heavy ion collisions, you sort of have the shear viscosity to entropy ratio sort of 1/4 pi or something like that. Okay, so now, of course, we want more, so that's great. This is all based on sort of basically vanilla ordinary fluid dynamics. In practice, people are using second order fluid dynamics, but the second order is not very important, actually. It's just the first order is really the thing. Okay, so sort of vanilla ordinary fluid dynamics. Now, okay, so now let's just talk about the trajectory of a heavy ion collision in the phase diagram, okay? So this is sort of showing the phase diagram of QCD. There's a temperature here, and then there's a baryon chemical potential here. So the trajectory that I'm going to be mostly focused on here is this very high energy collisions where the baryon number is very small. Okay, and so the trajectory of a heavy ion collision starts up here in QGP, quark gluon plasma, with restored chiral symmetry. Okay, and the temperature is about 350 MeV or maybe 400 MeV. Depends on where exactly you start. Okay, that's the initial temperature. And then you sort of sail down this axis here. What's known from lattice QCD? Yes? Question? Yeah? So what's known from lattice QCD is that there's a crossover transition, okay, at around 160 MeV. And then the system sort of develops order parameter or broken chiral condensate, Q bar Q, broken chiral symmetry. So now, okay, so that's the picture, right, of what's going on. Now, one of the things that has concerned me is that somehow this chiral symmetry and its breaking and pattern of breaking plays no significant role in the standard hydro model of heavy ion collisions, okay? In principle, there's a little bit, I mean, you're inputting the equation of state, and the equation of state from lattice QCD does, of course, know about chiral symmetry breaking and so forth. So you put that much in, but beyond that input, there's no knowledge about chiral symmetry in these simulations of heavy ion collisions, okay? And there's no knowledge of chiral symmetry breaking. So it seems to me a good place for improvement, okay, and to incorporate somehow the chiral symmetry and its breaking into the hydrodynamic description. Okay, so yeah, right. So okay, of course it's not crazy not to have the chiral symmetry in the hydrodynamics description, because in reality, the quark mass is not strictly zero, right? So if it were the quark mass and the pion mass were really zero, then everyone would be incorporating chiral symmetry into their simulations. They would have to, right? But at a finite quark mass, of course, this transition is really just a crossover. This description of broken chiral symmetry is only approximate and so forth. And so then it becomes a quantitative question whether you actually need any of this or not, okay? Broken chiral symmetry in your hydrodynamic description. Okay, and that'll be a lot of what concerns us. All right. Okay, so yes, go ahead. Yeah, please.
Can I ask a very quick question about the previous plot? So this dark line, the next one, sorry. Yeah, so this dark line that you have drawn, is this a first order phase transition line?
Yeah, so that's like a sort of schematic knowledge about the phase transition. So this,
right. So it's a first order phase transition between the confinement and the deconfinement phase. Do I understand that right? And these values of chemical potential can be experimentally accessed. I mean, so this is known, right? I'm asking. I mean,
so there's an experimental program at the heavy ion at the low energy collisions to push to study the regions of high baryon chemical potential and to potentially find this point, this so-called critical point, right? So now, and I won't really say much about it. You have to go, so you're limited there. So as you go down in energy, you're producing less particles, right? And also the kinematics understanding of the event is difficult to model, okay? Because, well, people are trying and they're trying hard, but it's certainly nowhere near as nice. The detectors are not as nice. There are not as many particles. The system doesn't live as long, on and on and on. It's actually quite difficult, challenging thing to run a hydro simulation in that regime. Nevertheless, people are trying to push out to higher baryon density and find this critical point, okay? I will be focused on this trajectory here. And there, the hydrodynamic description is great. Okay, there's lots of particles, it's high, and the detectors are amazing, and the whole thing is nice.
Right, okay? Thanks a lot.
Yeah, right, so I have worked on this part, but not today, really, okay? All right, so let's try and put into this theory, like if the quark mass were strictly zero, then you would really need to incorporate this chiral symmetry and its breaking into the fluid description. Let's start with that. Okay. Oh, sorry, one more slide first. Okay, so what is seen on the lattice? So this is really the trajectory. What people see on the lattice is they definitely see even though the quark mass is finite and it's not clear that chiral symmetry breaking should be important, they definitely see remnants of chiral symmetry breaking. And when you have two light flavors, then the symmetry group is SU2 cross SU2, SU2 left cross SU2 right, or O4. And they definitely see chiral symmetry in O4 scaling in lattice QCD. So that's really the real world. At real quark masses, they really see evidence for this O4 scaling or the proximity of an O4 critical point. Okay, and this is what I find quite beautiful lattice data. So they're plotting here the chiral susceptibility, or the second derivative of the partition function with respect to the quark mass. Okay, and they are plotting it. This is temperature on the x-axis, okay? And then they're changing the quark mass, right? And the green curves is the physical point here, okay? So that's this green curve, I tried to make it. So this is really the chiral susceptibility in the real world, kind of increases by a factor of 2. It doesn't look that impressive, but it's pretty impressive actually. I mean, increases by a factor of 2 or more over just a few tens of MeVs, okay? And more or less, and then what they actually show here is they reduce the pion mass, okay? And actually reduce the pion mass by a factor of 2, okay? And as they reduce the pion mass by a factor of 2, of course, the chiral symmetry becomes more important, okay? And the chiral susceptibility, rapidly sort of increases as you decrease the pion mass. So here's the quark mass being large, and here it being small, okay? And you sort of see this chiral susceptibility rapidly increasing, okay? Furthermore, even more impressive is that this trend, right? You can start to fit this trend, and the data isn't so good to make very strong on that claim, but nevertheless, this kind of basic expectation about how it increases, how much it increases, how the shape changes. You see how, the shape is clearly changing, right? Is all sort of consistent with the O4 scaling properties, right? So if you have a O4 transition and you were close enough to the critical point, then the chiral susceptibility would be given by universality, okay? And you would expect the chiral susceptibility to scale in this way, where it scales with quark mass with specific critical exponents, and Z is the scaling variable, that's T minus TC, and quark mass again with specific exponents. And that is somehow consistent with what is seen on the lattice, okay? And gives us, really, so at least we know in the real world, the O4 critical point, or SU2 left cross SU2 right, is there, okay? People are seeing it, they see its role, okay? And nevertheless, this O4 critical point is not really recognized in heavy ion collisions at all. Okay, really plays no role. All right, so hopefully that's enough motivation. Okay, now let's sort of go on and talk about hydrodynamics in the critical limit, in the chiral limit. Okay, so this is largely following not just Son, but some other people, and Son and Stefanov. Okay, so in the chiral limit, you would have conserved quantities. You would have, of course, the stress tensor, the U1 current baryon number. You would have the conservation of isovector current charge, okay, which is be the vector current with an isospin index, flavor index. And you would also have this isoaxial vector charge current, which is, written up here, okay, left minus right. So just as a moment of discussion here, the hat will always mean axial, okay? So every time you see a hat, it means axial current, okay? And if you don't see a hat, then it's not axial, okay? And similarly with the chemical potential. So if this chiral symmetry is broken, okay, then there's a order parameter, right? And the phase of the order parameter is usually parameterized in chiral perturbation theory by U, okay, this unitary matrix, and it is given by the Pion field, okay, which I write here, okay, and tau A are Pauli matrices. So the Pion field is like, in the limit of chiral limit, right? The Pion field is like T, the velocity and the temperature and the chemical potential and the axial chemical potential and so forth. And it should appear in the constituent relations that you're going to write down in your hydrodynamic theory, okay? So that's exactly what we're gonna do. We're gonna write down a theory in the broken phase for including these phase fluctuations or the Pion, okay? Now, well, as I said, right, in the real world, this chiral symmetry is only approximate, right? So you're going to include a mass term. So these Goldstone fields will decay at large distances. And so we're going to work that out. Okay, so we're going to write down a theory of SU2 left cross SU2 right superfluid. Fortunately, Damson wrote it down in 1999, at least at ideal hydro level. Okay, and that paper has about 3 citations, although it's extremely beautiful. Okay, so good. So now, so just to show the picture, okay, so we're going to work in this regime here. So there's different modes here. So if I look at long distances, right, these are the black lines, then the theory is in ordinary hydrodynamics, okay? And I'm showing here, you know, equilibrated hydro modes with wavelength who's much smaller than the inverse pion mass, okay? At shorter distances, then these modes of order the pion mass, okay, then you'll start to see the gold stones, okay? And those are kind of the superfluid modes, okay? If you go still shorter in distances, say momentum of order the temperature, okay, then you'll start to see the microscopic constituents that, you know, of the hadron gas. In particular, see, you know, pions, kaons, rhos, all kinds of other hadrons running around there, okay, and you know, they, you know, and including pions, okay, I mean pions with momentum of order the temperature as opposed to momentum of order m pi, okay. So, you know, let me maybe give some numbers here. I mean, so the typical momentum m pi is like, you know, 140 MeV, right? So it's pretty soft. The typical momentum, the typical momentum like 3T is like 600, 800 MeV. Okay, so in reality, you know, you don't have a lot of room here, okay? But nevertheless, it still exists. I mean, if the mass, the first bin usually in heavy ion collisions is the order m pi, okay? And it shows you that that's like small, okay? And the typical momentum is, you know, 800 MeV or so. And so you kind of have a factor of 8 between this hard scale, or maybe 7 or a little less, okay? Say 5, okay? Between this hard scale and this soft scale. Okay, so now the question I wanted to talk about in this talk is how do these superfluid modes contribute to the pressure and the shear viscosity and the diffusion rates of the normal fluid, okay? So the basic plan would be like to integrate out these superfluid modes and ask how they modify the transport parameters of the normal modes. Okay, all right. So let me just give a sort of preview here, right? So we'll show, I mean, we're gonna do exactly what I said. We're gonna integrate out this loop here of these superfluid modes, and we'll show that the normal fluid transport parameters have the following expansions in the pion mass, okay? So the bulk viscosity will have some leading bulk viscosity, which is independent of the quark mass, and then there'll be a correction, which comes from the superfluid equations of motion. Similarly, the shear viscosity has some piece and then some correction. And the conductivity, however, you know, will have a piece which goes like 1 over m pi, and then this will be the leading piece from the superfluid plus a finite correction. The expansion here in quark mass is not analytic, right? So it's it goes like m pi is like square root of m quark. And so you see here sort of 1 over square root of m quark, square root of m quark, square root of m quark. And this non-analyticity will come from the kind of superfluid loops, okay? Which is very much analogous to the long-time tails, okay? Where the correlators decay as fractional powers, okay? And here, very similarly, you're gonna find that these contributions will scale like non-analytically in the pion mass, in the quark mass. Okay, all right, so let's start. I'm gonna start now to work it out. So we're gonna go back to this picture. Okay, yes, go ahead.
Yeah, so I was just probably you will talk about this, but how unambiguous is the separation between superfluid modes and other modes, and there's some ambiguity in how you integrate out.
Yeah, I mean, so, well, you'll get divergences and you'll need to, well, I mean, it's a kinematic separation. And of course, at the boundary, you know, you'll have some overlap between these two descriptions, right? And that means that, you know, you'll get a divergence which will have to be absorbed into these other parameters. Maybe I can go on and come back to that in a little bit.
Okay, yeah, thanks.
Mm-hmm. I mean, so
sorry, just to clarify
yeah.
the point once. I mean, so, you know, I think here you are able to do this only because of the presence of, you know, the pion mass is non-zero. You know, do I understand that right? You know, had the pion mass been exactly zero, then this separation wouldn't have been possible, right?
So if I would say like this, so the separation between what and what, right? So
the fluid modes and the hydro modes.
The normal fluid modes,
yeah,
and
right.
the superfluid modes would not be, you would not be able to separate it out, right? So if the pion mass had been exactly zero, then the appropriate theory is superfluid, right? Is superfluid theory, not normal fluid, right? And it's only because the pion is massive that at long distances, the appropriate theory is ordinary fluid.
Right.
And that's why you can integrate them out. Right.
Right.
Okay.
But usually, you know, in the you know, just to understand this point a little better, you know, in the usual superfluid hydrodynamics, you know, there exists relationship between the two degrees of freedom in some sense, right? You know, if you take, you know, the chemical potential would be
yes.
In some way. So basically, I guess, the question is it, you know, so, you know, how does this mass help in actually performing the segregation in the usual hydrodynamic? I think maybe you'll get there, or maybe.
Right. I mean, so you're going to have to add some terms which are proportional to the mass, and then that, you know, normally in fluid and superfluid dynamics, you would have like the derivative of the phase is the chemical potential.
Exactly.
Right. And here you'll find that there's dissipative terms which make the phase appear explicitly and not just derivatives of the phase.
I see.
Right.
I see.
And so the phase will decay to zero at long distances. Yeah. Okay. Exactly. So that's where we're going. Exactly. So the phase will, well, I said it. Let's press on a little bit and then we can go on. Good. So you would start, let's start, before we start talking about hydro, let's talk about the partition function. So the partition function, you know, you would like look at first let's look at equilibrium partition function. And then you would have some contribution from the hard modes. And then you would have some contribution from these soft pion modes with P of order m pi. Okay, there shouldn't be a T there. Okay, and you would write down like the most general Lagrangian you could in 3 dimensions, incorporating this pion phase, and that would describe how, you know, these superfluid modes would enter into the partition function. So here the phase is this unitary matrix U. Okay, and now if I write down the terms which are allowed, okay, at lowest order you would just get like a 3-dimensional version of chiral perturbation theory. Okay, very similar action was written down you know, earlier for the normal fluids. Sorry, for the U1 superfluids. Okay, and so you have this first term which is gradient squared, and now because it's a mass, there is a mass, you can also add a term which is just proportional to the phase, the trace of U. Okay, and so if you expand with a mass term, okay, so if you expand it out, you'll have just a simple action, you know, scalar field in 3 dimensions. Okay, okay, the parameters F and M, they are functions of temperature, and you'll have to keep that in mind. Okay, and now if you want to use this action, right, you can go ahead and you can now, because of the mass, you can integrate this out, right? Just do this one loop thing, free theory, and you can get a correction to the pressure, which depends on this the mass. It goes like T times m cubed, and it goes like m quark to the 3/2. Okay. Okay, so you can integrate out these terms. All right. So now what will also be important for me is discussion. So these parameters, right, near the critical point, so near the critical point, these parameters depend on temperature in specific ways, okay? So the chiral crossover, in some sense, is like a transition from a normal fluid well above TC to a superfluid well below TC. And so these parameters, which describe how this parameter, order parameter goes, right, have known dependencies on temperature near the critical point. So in particular, okay, so they have universal O4 dependence, right? And so this F squared M squared, that goes like MQ psi bar psi, which is MQ to the T to the power beta, right? So all of those parameters, at least near the critical chiral crossover, and this F squared is like the correlation, kind of correlation length. Yeah, goes like T to the power nu, right? And so you know how these parameters depend near the critical point. Moreover, it's a Euclidean theory, so it's a great place for lattice QCD to contribute. So they can measure those parameters in really detail going forward. And I know that they're interested. Hopefully this paper will spur them forward, and they can go and measure these parameters near the crossover. All right. Okay. So now once you have the the Euclidean theory or the three-dimensional theory, it's a really with benefit of some smart theorists. It's a straightforward step to sort of work out the hydrodynamic theory, or at least at ideal hydro. So in particular, I'm following Jensen and Bhattacharya and Loga and many others. Okay, in particular here. Okay, so if you have the pressure, right, which now has these pieces, it has one part due to the chemical potential, and now it has one part due to the phase, then you could, differentiate the effective action with respect to the metric and the gauge fields and derive sort of equations of motion for the superfluid parameters. So I've written here linearized level. Okay, so I've expanded this U matrix, this unitary matrix, in terms of the quadratic order. Okay, and so the stress tensor really just looks like 3 copies of the U1 superfluid, and same with the axial current. Okay, that it's a sort of normal fluid plus a superfluid piece. Now in our paper we didn't make we also did this linearized approximation, but we also wrote it in terms of this field U in fully nonlinear form. Okay, and then finally you have this relationship which was alluded to between the phase, the Josephson constraint, which says that the phase is equal to the chemical potential. I will talk about it on the next slide where it comes from. Okay, and because you have a mass, the current will not be exactly conserved, but actually only this sort of partially conserved, right? So if we take a pause here, right, we see here this is the axial current. It's not exactly conserved, but it's proportional to the phase, right, on the other side. Okay, which will give somehow the mass term. Right, so about this Josephson constraint, maybe just one pause, like where it comes from, and one quick discussion. Okay, so I would say, once you have what's happening in a superfluid is that you have a charged field and it's developing a VEV, right? And so this expectation value has to be stable under the evolution of the system, right? And so what you have to have is that So in our case, the phase U is related to mu hat, okay, the chemical potential, because this field, Q bar right, Q bar left, is stationary under the evolution of the system. So if I compute the commutator of sigma with H minus mu n, okay, that needs to be 0, otherwise you won't develop a stable VEV. And then if you use like the transformation properties of the charges of sigma under the charges, right? You know, just that this generates the rotations, okay? Then you get here somehow, after just writing out this equation, you get that the time derivative of the phase that comes from the commutator of H, and these extra terms, right, which come from the rotational aspects of this Q's. Okay, and so you find after, you know, one line of algebra, you find that the derivative of the phase is equal to, in this case, the axial chemical potential, which involves now this unitary matrix. And if you linearize it, then you get like the Josephson equation that says that the time derivative of the phase is equal to the chemical potential. Okay, so maybe there is no mass term there yet, okay? It will come in the next second when you start looking at dissipative corrections to the Josephson constraint. Then you will find that, you know, the mass term will enter there. Okay. All right, so we have now the ideal fluid equations, right? Now, including the next step would be to develop the viscous corrections, right? And so let's discuss here. Okay, so so you have your ideal equations of motion. You have this partially conserved current, and then you have the Josephson constraint here. A lot of this was discussed by Stony and Stefanov for the tiny bit of from us, which was, you know, very much guided by Loga and others on their discussion of entropy, right? So now if you have these currents, right, you would expand it order by order in the gradients. So you would have here at first order in gradients, you would have the ideal current, and now at second order, in some sense, you have the conductivity, which looks very similar, and then you would add noise terms. And now in the Josephson constraint, you would start to also add some terms, right? So you would have here, the first says the time derivative of a phase is equal to the chemical potential. And now you would start to add sort of viscous corrections to the Josephson constraint. So the types of terms you could write down would be this kappa 2, right? Second derivative of phase. But you would also be just allowed to be just include the phase itself, right? Because it doesn't need to come with derivative of phase. You can just have the phase itself, but every time you do that, you pay a penalty and you need to incorporate the mass term here. So you would have now a new correction to the Josephson constraint, which depends on mass. Okay, and explicitly the phase as opposed to just the derivative of the phase. So if you look at this equation, you can see, right, because of this term, right, the phase is going to decrease to 0, right, explicit mass term, right. Now, what we also did using somehow the entropy analysis, which wasn't recognized in there, was to realize that actually this kappa 2 and by looking at entropy production, you know, we realize that this kappa 2 and kappa 1 actually need to be the same value, okay? And so actually the form of the viscous correction actually only has one parameter and not 2, right? And so, so by requiring entropy production be positive, we get this constraint between kappa 2 and kappa 1, which we call that they should be equal, and we call that zeta 2. All right, good. So now we have equations of motion. To reach equilibrium, you have to have this noise terms, and the noise terms are specified. And so now by the fluctuation dissipation theorem, and now you have sort of stochastic equations of motion.
Hello.
Yeah.
So Derek, in this slide, you're basically ignoring the energy momentum.
That's right. That's right. We did it kind of in appropriate limit. it's not important.
Mm.
We did it in the paper. We did include it in the paper. We did include the discussion in the paper. At lowest order, though, it affects the bulk viscosity, right? But not the shear. I mean, there's another contribution of this phase to the bulk viscosity. Right. Okay. Great. So of course you can look at the equations of motion of this phase, right? So a lot of people have done this, but let me just give my own spin on it. So of course you look at the linearized equations of motion, and you can find a dispersion curve for this mode in the linearized equations of motion. The wave has a solution of this form, which is second sound. I found a paper by Herzog and Son and Koftun, very helpful. Okay, and then of course the quasi-particle energy is given by this omega q, and what enters there is this v naught squared, which is the velocity of second sound. It comes as the ratio between this pion decay constant and the axial susceptibility. Okay, so that's somehow the pion velocity which is entering. And then there's this decay rate of this mode, which is a function of this two transport coefficients, which I had, zeta and sigma 2. So the decay rate has this form, I call it dA and dm, and dA and dm are related to the two transport coefficients that I had in the theory, zeta, sigma, and zeta 2. All right. So maybe just a 1 second discussion here about this pion velocity, what it means, okay? So of course, the equation of motion for the pion is just a simple, minimally coupled scalar. And, the current conservation law actually ends up just being kind of wave equation for the pion, okay? And so, yeah, this first term is the total axial charge, and it has kind of super component and then kind of a normal component. And both, the chemical potential is proportional to the time derivative of the phase, and both of them are, proportional to the chemical potential. So actually, if you look at this thing, the pion velocity actually has a very simple interpretation. It actually sort of says the ratio between the supercomponent contribution to the charge divided by the super plus normal contribution to the charge, okay? And so, and now near TC, of course, the super component becomes a smaller and smaller contribution relative to the normal component. And the normal component starts to dominate this thing. And so you get a kind of, intuitive picture that why somehow the pion velocity should go to 0 near TC is because it's, this super component is becoming less and less and less, okay? And the pion velocity just then really goes to 0. Right, okay, so, and that will be somehow helpful. Right, so now we're done. We have the equations of motion. We have a little bit of the discussion, right? So now we've talked about equilibrium. Now we're going to drive the system and calculate the kinetics of this set of superfluid theory. So we're going to drive this thing with some gravity, drive it out of equilibrium, okay? And now these things will be driven out of equilibrium a little bit by the perturbation, and we're going to absorb we're going to calculate how those weakly out of equilibrium fluctuations modify the stress tensor, right? And those modifications are exactly like the superfluid contribution to, the shear and bulk viscosity, okay? Okay, so the basic plan would be, to integrate out these hydro loops, okay? So you would basically evaluate this hydro loop, okay? Integrating out these green modes to find their contribution to the stress tensor. And that is how you would compute the correction to the bulk viscosity. I will follow, so you could certainly, we did it in our paper, you can explicitly do this loop and it's not complicated. I actually will follow a different approach here, which I prefer, and I prefer it for several reasons, which is to develop a kinetic theory for these modes, okay? So I would claim that such hydro loops, which are somehow of great interest, are always equivalent to developing a kinetic theory for these modes, and then using the kinetic theory. Okay, and the kinetic theory has many advantages. In particular, if the system is really expanding or very far out of equilibrium, you can still use it. Whereas such loop calculations, really, you can't. Okay, so let's do that. So let's develop a kind of, so we're driving the system. It's a stochastic superfluid. Okay, you can, if as you have the equations of motion, you can ask how this phase space density of these modes evolves in time, and that evolution of that phase space density is given by, you know, the kinetic equation. Okay, so let's just sort of say very briefly how it goes. So you know, I won't go into any of the details, but you have the fields of superfluid hydro, the phase and the axial current. The stochastic equations of motion are kind of matrix versions of the Brownian motion. They'll sort of have some ideal piece, some damping piece, and some noise piece. And now you can break up the equations of motion into the eigenmodes of the ideal piece and analyze what goes on and how the density of these modes changes in time. Okay, so the eigenmodes of this ideal piece are the propagating pions. Okay, they have this phi plus and phi minus. And now you could ask about how the phase space density is the squared density of this field. Okay, that's somehow what is the phase space density. So, okay, so you want to find an evolution equation for the phase space density of this second sound, or the pions. And so you look at the Wigner transform of this pion fields, and you have the equations of motion for these fields. And so you can ask how this Wigner transform evolves. And I guess not surprisingly, right, the phase space distribution evolves kind of follows a kind of Boltzmann equation, right? So the phase space distribution evolves according to this sort of typical Boltzmann equation. And what enters in this Boltzmann equation is, of course, this chirally and correct dispersion curve and the damping rate, chirally correct damping rate, which enters into the equation of motion. Okay, so if you ask what does this Boltzmann equation mean, it means that these pions are evolving with effective fluid Hamiltonian, okay, where the dispersion curve is you know, the on-shell constraint is given by that H, the Hamiltonian should be on shell, 0, and you have a specific fluid metric which incorporates the fluid velocity and the pion velocity into the equations of motion, and you can calculate the trajectories that the particles follow, etc., by just solving this equations of motion. Okay, so somehow that's equivalent to integrating out this superfluid loops. All right.
Hello.
Yeah, go ahead.
So I'm just trying to understand this Boltzmann equation. So I suppose there should be an f pi in the first term. It should be a del t f pi.
Yes. Yes.
And in the right hand side, why do you have omega q f pi minus t? Why is that correct?
Okay. Yeah. So first of all, there's an omega q on the left hand side.
Mm-hmm.
So you should divide through by omega q.
Okay.
Typically, right? And then you would find that f pi, the density of pions, approaches minus t over omega q.
Okay.
I mean, approaches t over omega q, which is the classical part of the Bose-Einstein distribution function.
Huh.
Right? So, I mean, if I pull out an omega q, I get f pi is approaching t over omega q.
Okay. Uh-huh.
Right? And that's the classical Bose-Einstein distribution.
Okay.
Right.
And so you've approximated to classical Bose-Einstein distribution because you are at high enough temperature and so on.
Right, because we're dealing with the fluid,
Okay.
right? And the wavelength of the modes of interest are so much longer than the inverse temperature that, you know, the classical approximation is appropriate.
And you're multiplied through omega q because omega q, you know, like vanishes. What is the,
what motivated me to multiply by omega q? If you write it manifestly covariantly, then the omega q sits there.
Huh, right.
It's P mu d mu is the Boltzmann equation. And that was the motivation. So
Okay.
if you do it in manifest, it's kind of like you have relativistic normalization of states is the energy, and that's essentially why.
Okay. And what do you have an explicit expression for omega q? What is omega q?
Yes, I gave it already. I went quite quickly. That's this thing, right? So it's omega q involves this velocity parameter, right? Which is going to 0 in e to dc, and then it's just sort of q squared plus m squared. M squared is not the pole mass, but so-called the screening mass. And again, all of the parameters in the dispersion curve, this v and this m, those are all Euclidean quantities, and all of them can be determined from the lattice, right? And then the damping rate, you know, is involves then these dissipative coefficients of the superfluid theory. So all of the of course, we derived the Boltzmann equation from the superfluid theory, so you just get the same results really as the superfluid theory. Okay.
So this point number 3 is the statement that you are thinking of freezing some normal fluid background and integrating out the pion distribution effects on that.
Yeah, I think so. I mean, the wavelength associated with the normal fluid is very much longer than this Q, right? I mean, the wavelength Q is a short, it has momentum of order m pi, and the wavelength of the normal fluid is very long, right? And so essentially it's kind of a background metric in which these particles propagate.
Okay. And delta mu nu is the projection to the transverse to the U space?
Yes, yes. Okay. Yeah. So it's gravity in a certain sense, right? Because, you know, well, it's a specific metric. Okay. Good. So, I mean, once you have said this, that this, at least with the kinematic approximations that I've outlined, that, you know, the superfluid equations are equivalent to this sort of Boltzmann equation, then it's kind of standard technique to calculate how the transport coefficients depend on these modes. So the basic spirit would be, you know, turn on a driving term in the Boltzmann equation. Here's the kinetic equation again. There's the change in the kinetic distribution tries to evolve to equilibrium, but there's a driving term driving it out of equilibrium. Then you can solve for the correction, you know, to this distribution due to the driving term. And then once you know this distribution, that should be delta f pi, then you can calculate the corrections to the stress tensor. So of course the stress tensor has some pieces, it has some pressure from the superfluid and some contribution from this kinetic terms. And so if you know this distribution of this 2-point functions, which is the phase-space distribution of pions, you can go ahead and evaluate their contributions to the stress tensor, okay? And so the final result is somehow that the pion contribution to the stress tensor has a sort of very specific form. So if you take the hydro expression for the stress tensor, and then if you express it in terms of the 2-point functions, you can write it as an integral over the phase-space density of these pion modes, okay, which then determines the T mu nu from this pions. Okay. All right, so which determines the corrections to T mu nu. So here's sort of say the expression you have. Yeah, go ahead.
So this expression would be the same as what I would get if I just did it from the field theory, where I just calculated the energy momentum carried by the pion.
Yes, yes, it's derived from the field theory expression, right?
And
with some kinematic approximations associated with the scale separation.
And the statement is that, you know, like the field theory is very well approximated by this kind of a kinetic theory consideration, and gives
at least in this regime where the background fluid is very long and the pion contribution is somewhat shorter.
Mm-hmm. But
right.
Are you also assuming that f pi is also not too small? Or
it's also that it should be in the classical regime. Yes. Right. So indeed, this f pi, it goes like T over omega q. And omega q is assumed to be much, much smaller than T. So T is kind of the cutoff, really the microscopic cutoff. And because we're doing hydro, this omega q should be much smaller than T, which means that f pi is large. Yeah.
So this is really a very good approximation at very large temperatures.
Yeah, so, and that's why there's not a lot of room here, okay? Because if you want to make the temperature large, but you still want to be in a broken regime, okay? And so there's not a lot of room here. And maybe so there's not a lot of kinematic window, so that you definitely want to go beyond this, what I've done here in reality. And I basically including the order parameter more explicitly in the hydro equations of motion, right? Because as it is now, I can only go somewhat close to TC, not very close.
Okay.
Right. Yeah, but of course I want T to be large. Yes, I want T to be very large.
So am I understanding this right, that in this approximation you are basically ignoring any kind of pion-pion interactions or collisions and scattering?
Yes,
and
of the soft pions.
Yeah, of the soft pions, yes, indeed.
Right, so of course the hard pions are scattering all the time, right? But the soft pions, actually, they don't scatter with each other because it's all derivatively coupled. So it's much more likely for them to scatter off a normal piece of the fluid, which includes some hard momenta.
Okay. So this is really scattering with the fluid modes, fluid background.
The hard modes. Yep. Mm-hmm.
Okay. Thanks.
Right, and all of that scattering is incorporated into these dissipative parameters of the superfluid theory. Right. Okay, so so now you get expression for the bulk viscosity. You have some contribution from the hard modes, and then you have this contribution from these pion modes. So it's a little bit involved here, but at least let me state it. Okay, so it depends on. The result depends on the dispersion curve. So this is the velocity of the pion and its dependence on temperature. And this is the mass of the pole mass of the pion and its dependence on temperature. And then you can do this integral, okay, and find how the result depends on this pion dispersion curve, okay, pion contribution. So the separation here, so the integral is divergent, right, at the upper limit. This comes to what was asked before. And of course, you need to take that divergence and bury it into the definition of what you call zeta 0. So after doing that renormalization of zeta 0, you get basically the full expression for the normal bulk viscosity. Okay, so I'll try to tear this down a little bit and look at this formula a little bit and say what it means. Okay, so first of all, it depends on these parameters, okay? It depends on the dispersion curve, the velocity, and the mass. It also depends on the ratio of the, actually funny, square root of ratio between the dissipative coefficients, the dm and dA, the two dissipative coefficients in the superfluid theory. And so now you can do it also, you get finally the results here. So for not just the bulk viscosity, but the shear viscosity and the conductivity. And so you sort of see what was advertised in the beginning. You have some expressions for how the parameters, how the bulk viscosity depends on the Pion parameters, how the shear viscosity depends on the Pion parameters, and how the conductivity depends on the Pion parameters. Now, maybe most important, honestly, is the conductivity. So you see there, this thing appears like 1 over m pi, right? It's very clear why, is because the pion itself is a gold stone, right? And it carries also the charge of the theory. So the transport of charge is dominated by this goldstone contribution, right? Which is much larger than the other contributions to the transport of charge. All right.
Hello?
Yeah, yeah.
What is MP here? M subscript?
Yeah, I'm sorry. So it's just a product. It's the pole. So the M is little m without a p is the screening mass, and this is the so-called pole mass,
Okay.
and it's the product of the velocity and the mass squared. All right. So if you, in some sense, the pole mass is what you think of as the mass, right? Okay. Right. So anyway, it's how the pion depends on the pion pole mass depends on temperature. All right, so this is kind of neat. I would like to extrapolate these formulas close to the critical point. And so, of course, so I want to push these formulas close to the critical point. But you can't, with what I've done here, you can't go too close to the O4 critical point. So the O4 critical point involves this Q bar Q order parameter with flavor indices, okay? And the order parameter involves basically an amplitude, okay, and a phase. And we've only included the fluctuations of the phase. Like if you get too close to TC, then you would also need to include the fluctuations of the amplitude in the order parameter. And write down a hydro theory involving this O4 field, okay? And so we've pretty much done that now, but I won't talk about it. At the moment, I will just take these formulas near TC, focusing on just the fluctuation of the phase, but not too close. Okay. So for simplicity, I'll take this R parameter to 0, okay? And then you have some somehow simpler expressions. It doesn't really depend strongly on R. You can change it between 0 and 1 and nothing much changes. And now you can look at these parameters, and most of the dependence on temperature is given by the O4 static universality properties of the phase transition. So as I said, these quantities are all determined by the Euclidean theory and have known dependencies on temperature near the critical point, right? So that's all given by the static properties. So if I look at such expressions, what's missing is somehow this last part, which is how does this axial charge diffusion coefficient depend near the critical point? Okay. But here you can use sort of say dynamic universality. So the pion is the order parameter, right? And so the relaxation rate for the pion, should track the order parameter, which is given by dynamic universality. So the pion damping rate, which is this dAq squared diffusion, should go like the order parameter damping rate, which is given by the dynamic universality class of O4. So, and that exponent is known it goes like the correlation length to the minus z, right? And so you can actually find predictions for how this diffusion coefficient of the axial charge should depend near the critical point. So in particular, this set of reasoning says that this diffusion coefficient depends like t to the minus nu 2 minus d over 2. Okay, so you actually know somehow how the dissipative parameters go right near TC. Okay.
Hello?
Yeah,
Sorry.
please.
So this dA, as you're saying, it's related to the diffusion of the axial charge.
Yes.
And you can probably estimate it by some kind of Kubo formula kind of calculation. But what about this dm? What is the physics that determines dm? And
yeah, so
small or large? And
yeah, so first of all, it's between 0 and 1. Okay, sorry, the ratio. Let's call this R. Okay, R is the ratio of dm over dA, right? So it's the ratio between. Where do I have it? So of course, yeah, let me say it like this. The damping rate at small momentum has two contributions, right? One is proportional to q squared, and one of them is proportional to m squared. So the total damping rate is some constant, I mean, just from counting, is some constant times q squared plus another constant times m squared. And the dm is the constant in front of the m squared, and the dA is the constant in front of q squared, right? And so it's because you have a finite mass that the pion field is not, the damping rate of the pion field is not just proportional to q squared, but also has some contribution that goes like mass squared, right? Basically, we know a lot about it. So the ratio, it's not a huge issue. So the ratio is this actually, we know this constant R, which is the square root of the ratio, has to be less than 1, okay? And if you vary these formulas between 0 and 1, you'll find that these things don't change very much, okay? So it really is not a significant issue from a practical sense. We also did a computation of the pion damping rate in chiral perturbation theory, and we found that R is actually square root of 3/4. So it's kind of an order 1 number, right? Mm-hmm. Between the mass and the momentum damping rate. So again, I think it's not such, so we took it 0, but you could have made it a half. That would have been a better choice. Okay. But you don't get any real qualitative changes, or maybe square root of 3/4 would be the best choice, since that's the only theory where it's been calculated. Okay.
So is it, is it of the order of V0 or something? Like, is it?
Yes. So basically near TC, this dA and dm should approach the same, have the same universal critical behavior. And so actually the ratio should just be a constant near TC, which I am not prepared to, really defend at this moment. Okay. So let's more or less forget dm, okay? But again, I don't think it's an issue.
I'm just asking, is dm a static quantity? Like, is it?
No, it's not. It's a dynamic quantity.
A dynamic quantity, right?
It's because it's the damping rate of pions, and right. So the pion damping rate has, again, just expanding at small momentum must go like q squared, and then a contribution that goes like m squared.
Okay, so it is something that requires a real-time calculation or a
absolutely, right. So we finally get kind of the expectations near T of what we expect these transport parameters to depend near TC. The bulk viscosity has some bare contribution, and then there's a part that decreases. Oh shoot, this has a misprint. I'm sorry. This 4 is wrong. I'm sorry. Anyway, this number is correct. I mean, and this statement is correct. So we find that the bulk viscosity sort of decreases sharply near Tc, somehow as T to the minus 0.81, okay? And we somehow find that the shear viscosity sort of grows slowly as T to the 0.19. And perhaps the most important result is both of these contributions are fine for what they are, but you see they're added to this other piece, right? And so, well, yeah, so this is, and actually this other piece is probably larger. No, more than probably, it is larger. And so it's kind of some correction, and we know how it depends on Tc. Perhaps the more important contribution is the charge diffusion. So here, because of the pion is dominating the transport, this pion, the conductivity, the pion contribution, the superfluid contribution dominates the coefficient. And there's no, well, there is a plus sigma I0, but that's subleading. And so somehow this is sort of, say, the full expectation that near Tc, the conductivity should then drop with a specific exponent like this 0.55, right? And go like square root of m quark in the denominator. Good. So let me, now I want to go to one more back to heavy ion collisions and ask if there's any evidence for this superfluid behavior in heavy ion collisions. Okay. So any more questions? Actually, I mean, I just substituting these numbers, getting these things. Okay. In particular, any more questions on this? Or I sort of say, I think it's relatively clear as the pion is dominating the transport because it carries isospin charge and it's nearly free. And it's decreasing near Tc essentially because the velocity is decreasing near Tc, right? Okay, so back to the heavy ion data. So, I would really like to find some evidence for this chiral crossover in the heavy ion data. And so these are fits to the heavy, and what I'm going to say now is not universally agreed on in any sense. Okay, so should understand that it's speculation. Okay, so you have here the spectrum of pions and kaons, and protons. These are yields from heavy ion collisions, the yield per momentum per rapidity. On the x-axis, we have momentum. Okay, and this is a hydrodynamic fit to those measured spectra, okay? And so, and just to orient you a little bit, so the typical momentum is like 700, 800 MeV, okay? And that's this black line here, right? And certainly by the time you get to the typical momentum of pions, those are not superfluid pions. Those are just regular pions that are produced in the heavy ion event, okay? If you get P much smaller than the typical momentum, okay, then, that would be the regime where you would start to look for some fluctuations of the order parameter. You would look down here and ask yourself whether you could describe these soft pion yields with P. So again, M pi is 140 MeV. It's this first bin, right? So the data is sort of running out of room there a little bit. That's going to change, okay? But anyway, if you ask yourself, where does the hydrodynamic fits fail? They almost all fail, okay? Down here at sort of small momentum of the pions, okay? Where P is of order 300 MeV, 400 MeV, 200 MeV, okay? P of order M pi. And honestly, this, as I said, this is not broadly agreed upon, but honestly, I think this is it, right? I think this is somehow evidence for somehow the pion dispersion curve being modified near the chiral critical point. So the pions are Goldstone, because the pions are Goldstone bosons, you can expect an enhancement at low transverse momentum. In particular, if I look at this Bose-Einstein factor, so the Bose-Einstein factor is, this thing, and near, this is for soft pions is T over omega Q. And since the velocity is going to 0, we expect an enhancement that basically, goes to infinity, okay, since the velocity gets small near TC. So I think, I don't know, I'm probably alone here, but I think that this might be evidence of the critical point. There's a lot to do here to sharpen up the predictions for what you expect for these yields. What do you expect for the variance in this yield? So they can measure not just the yield, but also the variances and also the correlations between these soft pions, especially with some new detectors which are proposed, which will fill in this region very carefully with high precision. And well, okay, so that's definitely a good place to use this hydrodynamic theory going forward and to try and fix that, okay? All right. So I don't know if there are any questions on that. It's mostly speculation, but.
Sorry. What is the typical value of this TC? I mean, like, in terms of
Typical value is 160 MeV.
60.
Right. Right. Yeah. Right. And so the typical momentum is here, and this is sort of well below typical. And the thing is, why I find somehow this is a challenge for the hydro is because, yes, they have parameters, and yes, they can change this thing, but you see, it's only in one region of momentum. So they can change these curves, move them, but to change them in one particular momentum bin or a couple momentum bins is quite difficult, right? And so, yeah, so that's why I find it somehow plausible that you need a new theory down there to describe this spectral change. Okay.
So Derek, you had these various parameters in your superfluid theory before you integrated out, dA, dm, and the static parameters, the V naught.
Yeah.
So what do you think is the easiest to see in experimental data?
What is the what?
What is the easiest ones to see? What are the first ones to see?
Yeah, I mean, I actually think, well, I would think that this dispersion curve is the simplest thing to see, quote unquote see. And that's what I mean, the yield of these pions in a thermal bath is somehow just, T over omega Q, right? And omega Q is the static properties of the pion. Omega Q is the dispersion curve, and it's determined only by the equilibrium properties.
So this would give you an idea of what you call as V naught and M, the pion
Exactly.
velocity.
I mean, keep in mind, I'm not saying that we know it yet, but yes, that's the idea.
Okay. Mm-hmm.
Right. From those yields, and more experiments that we should try now and predict. So my current plan is to somehow predict those yields, and then the next step predict the sort of variances of those yields, which also should reflect the sort of critical behavior. And once you've fixed whatever parameters you have to predicting the yields, I mean, so to getting the yields correctly, then the variances are then predictions, right? Real predictions. Okay, so I bring to my summary, okay? So I had this picture, there's sort of ordinary hydro, which are these black lines, longest distance, we have the superfluid modes, and then we have the hard modes. And I try to use the scale separation. And in the process, we wrote down the appropriate SU2 left, SU2 right superfluid theory. including the nonlinear forms, viscous and mass corrections, noise, etc. Okay. So maybe that was well known to some, okay, especially in this group, okay, but it was useful for us to write it all down. And then we used this superfluid theory to develop a kinetic equation for the soft pions. And that kinetic equation can really be used, in particular, potentially for simulating the events, or Ravian events, okay? We use this kinetic equation already to determine how the transport parameters depend on mpi by solving the driven kinetic equation or integrating out the hydro loops. And I would like to send that message home that whenever you're integrating out a hydro loop or something, you're really just doing kinetics in some sense. And finally, we should, I've only discussed the fluctuations in the phase, but in general, one should develop a theory for the order parameter, the full O4 order parameter, which includes both the amplitude and the phase. And you should write down a hydro theory for that, which again, may be one of those things that someone in this group knows, but I haven't seen it completely written down, but we're well on the way with that. So I think there are exciting hints of the chiral crossover in the data, which makes me really kind of new excitement actually in heavy ions. And finally, thank you and stay safe.
Thanks, Derek, for that wonderful talk. If anyone has any questions for the speaker, they may ask now. Okay, so if no one has...
Yeah, no, I just have one more question. So,
yeah.
In this whole discussion, like, what is the role of fluctuations? Can I, I mean, you wrote down some kind of an effective Brownian motion with both dissipation as well as some noise.
Yeah.
But what role does noise play in, let's say, in final expressions that you got about
yes.
the pieces and so on?
Yes. Let's see, is this okay? You can still see my slides, right?
Yeah.
Okay. Yeah, I mean, it was essential, right? Without the noise, you just have dissipation. So let me go, right? And then the field just damps down to 0, right? The Pion field, right? And otherwise, with the noise, so look at this Boltzmann equation, right? If you didn't have the noise, you wouldn't have this T there, right? Right? And then the phase space density would just die down to 0, right? But because you have the noise, right, you're constantly like feeding it back. And now the phase space density approaches the equilibrium 1. Right? Right. Again, this T is exactly from the noise, right? It's 2T eta, right? And that T is exactly coming from the noise.
Okay. Yeah. Thanks.
So it's essential for equilibrium, right? Somehow, right?
Okay, any more questions? Okay, if not, we'll thank Derek once again. And yeah.
So sorry for going a little too long. I appreciate the time.
Yeah, that's okay. That's okay. Yeah, thanks, Derek.
Okay.
And we'll see you guys next time.
Thanks a lot. Thank you.
Thank you.
Thanks, Derek.
Okay. Be well all. Bye.
Bye.